guess is where all the new stars form. So if you look at our galaxy, the old stars are much more spread out. They're flattened. There's still some rotation, but they're much more spread out than the galactic plane. It's the young stars that are in the galactic plane. And our star at 4.5 billion years actually counts as young. You know, to be old, you got to be more than about 10 billion years old.
Well, so I will be forever young.
That's right.
Yeah. All right. Hey, I went ahead and clicked on the button to go live. People are still seeing our introductory banner, but we can keep up our banter for a few more minutes, which some people have said they enjoy in the background until we officially start. So, speaking of old and new stars, one of the Science News articles I want to talk about this week is related to that. So, juicy.
Magnetar?
I'm sorry, what?
The Magnetar?
No. I want to talk about the star that has been given the name of the accident.
Yes, I just glanced at that article. Just
yeah, it'll be fun. We'll talk about that in a few minutes when we officially get started here. Let me go ahead and go live with the video. Abby said that she would be calling in using her phone. I hope she's not having troubles with that. All right, here we go. Now I have to resize my window to make sure it all fits in the YouTube. That all seems to work. Good. All right, now I'm going to open up my own copy of the YouTube stream so that I can chat with people. Hello, people. If you're already watching, welcome to Sidewalk Science. And let's see.
we're here. Except we don't have a sidewalk anymore.
Yeah, it's kind of a legacy name.
Yeah.
Are we going to get back there, do you think?
You know, it would be fun, I
It would
think.
be.
Not instead of this, but in addition to this, perhaps.
Yeah, absolutely.
Absolutely, yeah. It'd be fun. But then again, I think that's next summer, hopefully.
Spring, March, April.
It's still nippy in March and April.
Yes.
Not with global warming.
What are you going to do about your Massachusetts annex if you have it on the sidewalk in Chicago?
Hi, Cindy. Hi, Margaret. These people have come in to the right room.
Well, I just published the YouTube link on Meetup, but you know, we're pretty accommodating. We can have people watching.
That's the same as saying we're easy.
Well, yes. Yep.
Perhaps Cindy and Margaret are using a link that I forwarded to them. Maybe that's a different link, but
Oh,
it's
that
fine.
could be. Do you
It's
know
fine.
Cindy and
I'm
Margaret?
using YouTube.
Do.
Okay.
YouTube, yeah.
Yeah, you're welcome, Cindy and Margaret. However you were able to join us, we're glad that you're here. And let me get back and look at my
And Margaret.
YouTube stream here.
Nice.
Abigail. Hey, Abigail.
How's everyone doing?
Fine.
Hi, Abby. It is great to see you today.
Good seeing you as well. I will probably be rejoining you a while on my phone, but for the time being, I'm here on my laptop. Hang on a moment. I'm going to try and reduce the glare here. Here we go.
Your glare has been reduced. So are we live and doing things now?
Yeah, I'm just telling folks who are viewing us online instructions for interacting with us via typing.
So,
So what's new with you, Abby?
I started teaching again this week.
Yeah, good.
I already have a student out with COVID, but the college is keeping on top of it, apparently, which is good. And the streaming technology occasionally works. I was very impressed with it the first day. And then the second day, it started timing out on me for reasons I wasn't quite sure about. Maybe it was my fault, maybe it wasn't. But it is something that I actually really want to have be as perfect as possible.
Sure.
Simply because if I'm going to have students in quarantine, being able to catch the streaming lectures is really important.
Yeah. How? So is that the only way you're teaching? Is remotely via video?
No. I'm teaching in person. So most of my students are showing up in class, but because some people will undoubtedly be in quarantine from time to time, the college has set up all the classrooms with streaming capability. But then, of course, you have to learn how to use it. And, and this is the kind of thing where there's really no substitute for experience,
Yeah.
which means you make a few mistakes along the way. But anyway, so those have been my adventures for the week.
Well, we're glad you're here. Welcome to Sidewalk Science. We've been doing this for a little over a year now, and we have settled, at least for the time being, on a standard format where we begin by talking about some science. May the flying spaghetti monster bless you.
Mute if we're not talking. We should mute.
Yeah. In any case, our standard format is we start with a little bit of science news, and then we move on to talking about a deep dive science subject, and then after that, we have a discussion. Almost always the discussion is about that deep dive topic. So, without further ado, let's talk a little bit about some science news. Those of you who may have joined a little bit early heard me comment about one of the articles I wanted to mention. Let me pull that up here. It's, back in the Dark Ages, there was this concept of something being born that was unflatteringly called an accident. And I've known people that have identified as accidents, but I think that they're, to a person, they're wonderful people. So being accidental is not necessarily a bad thing. However, astronomers have recently identified an astronomical object that has been discovered by an amateur astronomer combing through some data made available by NASA and the European Space Agency, I believe. And combing through this data, he spotted an anomaly in a infrared signal that corresponds to something relatively warm moving through the sky. But it had some uncharacteristically peculiar properties, and it was discovered by accident. So it's been called the accident. And apparently it's something known as a brown dwarf. A brown dwarf is an intermediate stage between a star and a gas giant like Jupiter. It's really, really big compared to Jupiter, but it's not quite big enough to have its own sustained nuclear fusion and give off a lot of energy by fusion. It does, however, still have some heat left over from its gravitational collapse, and occasionally they may fuse things like tritium, some of the rarer elements in the universe that are more amenable to fusion. In any case, this particular brown dwarf doesn't match the spectral classification of other brown dwarfs that have been discovered, and it seems to be because it's much, much more ancient. It may date from a time period near the beginning of the universe in terms of the Big Bang cosmology.
Shouldn't, Scott, sorry,
Yeah.
shouldn't we now be calling them brown size challenged, mass challenged objects?
I think that would be a more politically correct, title for it. We might be able to propose that to the American Astronomical Association or whoever it is that names these things. But the brown dwarfs are sort of failed stars. I don't want to make them feel bad about themselves, but they're kind of failed stars and failed planets. They're kind of in this in-between region. But this one seems to be mostly comprised of hydrogen and helium and really nothing else. So there has been an ongoing program in the astronomical community to look for what are called population 3 stars, the oldest stars in the universe, which are thought to have been comprised of only hydrogen and helium because that's really all that was available. Well, this might be sort of a population 3 brown dwarf. It may be one of the most ancient things we've ever seen, and it's only about 50 light years away from us. So that was pretty interesting to me.
Note that it's not bigger than Jupiter. It's more massive than Jupiter. But these objects are comparable in size to Jupiter. They don't get bigger as you pour more stuff into them. They actually get a bit smaller.
Gas is pretty compressible.
Well, it's at that point, it's the electrons in the core that are compressible. It's held up by that Pauli pressure I keep talking about.
Yeah.
Yes. Everybody can tune in to an episode from a couple of times ago to see John talking about Pauli pressure and his putative new force of nature.
No, it's an old force of nature.
Oh,
We've
there
known
we
about
go.
it all the time. It's just that the quantum field theorists don't like to think of it as a force, but it's a real force. You can measure it.
Well, there was another one about stars that caught my interest, and they were looking at a pulsar that had a period of like 16.3 days, and they were looking at it going, what is this? So they used a pair of radio telescopes to look at it and discovered that part of the time the energy was coming towards us and part of the time the energy was going away from us. And they said, well, all of our previous ideas about it have just gone away. And so we're thinking about it as being a magnetar. Now, I don't know anything about magnetars, so I leave this up to you guys. What the heck is a magnetar other than a goofy magnet?
A magnetar is a neutron star with a magnetic field so intense that the magnetic pressure affects the dynamics of the star. And they do all sorts of crazy stuff. They have rearrangements of their magnetic fields that release so much energy that you can see them from megaparsecs away, and yeah, they're quite energetic objects, and the reason is because there's so much energy in their magnetic fields.
So what would be the relationship between the magnetic field and the speed of rotation of the star?
Well, if you have a magnetar, what happens is that it radiates long wavelength radio so efficiently that it slows down very quickly. The millisecond pulsars that we know appear to be recycled. Pulsars are probably born as millisecond pulsars, but they're hard to catch when they're that young. So the millisecond pulsars we know now seem to be recycled pulsars that have lost most of their magnetic fields and therefore, and then gotten spun up by accretion from a companion to 600 hertz is typical. And that's You know, that's the nature of the fast ones we know. And those are interesting
35-day
because
one is really weird.
what?
The 16.35.
Yeah. Oh
day
yeah.
is very weird.
Yeah. Yeah. You know, we thought it was pretty weird when I nailed down the discovery of a 2-minute one. But that was, you know, almost 50 years ago. Now we know about much slower things.
So we have a couple other interesting things related to biology. One of the news stories I saw was that there was an analysis done of evidence about the fossil record and speciation rates, and they tried to correlate this both with climate and with, strangely enough, altitude. And they found, this one study found that the speciation rate seems to be more highly correlated with geographic altitude compared to lateral distribution across different climatic zones. So mountains and deep valleys may be more relevant to causing boundaries between populations that evolve independently. That may be more relevant than previously expected.
Well, altitude is not a fixed quantity, right? I mean, land rises and falls.
Right.
You know, Himalayas are pushed up. They weren't there forever. They were pushed up. So altitude is not something that stays constant with geological time.
Right.
The top of Mount Everest is marine limestone.
Right.
It's been pushed up. Yeah.
So, which was apparently that kind of fact was something that perplexed.
I have my glasses, please.
Perplexed Leonardo da Vinci, among others. That you could find seashells on mountains, and you can correlate that with stories of the Great Flood that swallowed the earth and was on top of mountains and left seashells and whatnot. But there are more scientifically justifiable answers now that are supported by evidence about land rising and falling. But the rates at which land masses and mountains rise and fall tends to be relatively slow, even compared to the rate of speciation. Now think about Homo sapiens. We've been around for about 200,000 years. Well, 200,000 years in a typical geological context is a minuscule amount of time.
Yeah.
Did anybody else have any?
Valleys cause a certain amount of isolation between neighboring groups. I know as a Scot, we lived in valleys, and if you went the other side of the mountain, they were deadly enemies, and you just beat on them. And of course, if you went south, you beat up on the English. Sorry, Mike, but we. So would this have something to do with it? You know, the isolation relating to speciation?
Yeah, I didn't read the study details. I read a synopsis of the study, but it seemed to be what they were proposing is that, as we all are, or most of us probably already know, as you go up a mountain, you get into different climatic zones. So there's a rule of thumb, and I forget it at the moment. I apologize. It's something like every 1,000 feet is like 200 miles of latitude, something like that. There's this rule of thumb about as you go up in altitude, for every certain amount of altitude you ascend, it's like changing your location towards the North or South Pole. And that's why you can find essentially boreal, boreal forests lower on the altitudes of mountains, and then coniferous forests as you get higher on a mountain, while you also see the same kind of speciation differences in fauna, in living animals as well as plants. And the speculation proposed by this article, after studying climate versus altitude, is that altitude seems to be a big indicator of sort of a speciation driving force. All right, anybody else have any science news before we move on to our deep dive topic? All right, well, I will introduce to you all Dr. Mike Albro, who has worked at Fermilab as well as CERN, and he has been most recently working on the Large Hadron Collider. Some of the experiments associated with that particular device, and I won't tell any more about it because Mike is here to let us know. I'm going to have to make sure I've got the right device selected for our YouTube stream here. But Mike, before you change your slide, make sure that you get an okay for me that people have been able to see it. Well, I'm going to work on that in the background while you start talking.
Okay, can you see my slide now? My slide number 1?
No, not yet. I'm working on
Okay.
working on getting that slide to display.
All right.
I can see it.
Yeah, people on Zoom can see it, but the people on YouTube can't. So
I'm on YouTube and I can see it.
oh, you're on YouTube?
Uh-huh.
Well, so am I, and I don't. But go ahead, Mike. We can catch up here with.
All right. So yeah, so I'm sure just about everybody will know everything on this first slide, but I thought I should start right at the beginning just to introduce some things like the atom, which you all know and love, which has a nucleus in the middle, which is actually much, much smaller than it shows on this cartoon. It's actually about 100,000th the size of the atom, but that's hard to draw. So they draw it like this. And electrons are going in a cloud around the nucleus, which is made of 2 types of particle called protons and neutrons that are not fundamental particles because they're made of smaller particles called quarks. And the protons and neutrons are made of 2 types of quark mainly, which is they're called up and down, silly names, but that's how they got their names. And a proton has 2 ups and 1 down quark, while a neutron has 2 down quarks and 1 up quark. And that's what makes a difference in their charges. The quarks are actually stuck together by exchanging particles called gluons, and I'll get to that. And that becomes important when I talk about colliders. Now, at Fermilab, we discovered that 2 much heavier unstable quarks called the top quark and the bottom quark. And there are 2 intermediate ones called charm and strange. We like to make up these sort of names, but they have some history with them. And the next slide, and how do I get the next slide? Okay. The next slide. Okay. So this is now showing that we have a top left. I don't know if you can see my arrow. Maybe you can. So those are the up and down quarks that we know and love. They make up protons and neutrons together with an electron. And these 3 things make up all the matter that we know, basically. But we found more. We found that there's a version of the electron that has no electric charge. It's called neutrino, and that's here in this green box. And as I mentioned, the top and bottom quarks were discovered at Fermilab. They're very heavy, especially the top quarks, very heavy. And there are heavy versions of the electron and the heavy other versions of the neutrinos. And then my story is going to be about proton colliders, which discovered the top quark and the W and Z bosons here, which are force-carrying particles, a bit like the photon, which carries the electromagnetic force, but they, unlike the photon, which is massless and gives infinite range to electromagnetism, W and Z bosons are massive, and that gives a very short range to the weak force that they work with. And here's the gluon that sticks quarks together inside protons and neutrons. And then the Higgs boson put off to the side here. It's rather different from all the others, a very special one, the last one to be found. Now, this looks like a pretty neat sort of table of the particles of matter that we know, but it's only a few % of the stuff in the universe. There's dark matter and dark energy, and we don't really know what these are yet. We're looking for particles of dark matter. This Higgs boson here was discovered at CERN in 2012. I mentioned Fermilab participation there. By the way, I'm working at Fermilab, which is, as you probably know, in the western suburbs of Chicago. So now the next slide, I start to get into talking about the colliding beams, colliding proton beams. And starting from 50 years ago at the so-called intersecting storage rings at CERN. In 1969, that's when I did my PhD and moved to CERN as a postdoc. And at that time, the highest energy collisions we had between particles were with two machines. One was at CERN Geneva called the Proton synchrotron, at 26 GeV energy. GeV is a unit of mass or energy, and the proton mass is about 1 GeV. So this is like 26 times the proton mass. The proton's going pretty fast at that energy. And then Brookhaven on Long Island in New York had one slightly higher energy, but basically the same. And these machines were sending beams of particles from accelerators, hitting a stationary target. Could be a metal target or a gas target or whatever. But that's extremely inefficient. And here's a little cartoon analogy to that with these little cars. And I stole this from pixie.org on the web. Now imagine you have a beam proton that hits, say, a car, imagine a car that hits a stationary car. Now, if the car is stationary and it's got brakes on, there'll be quite a bit of damage to it. If the brakes of this car that's hit are off and it can recoil, it's pushed back and it carries momentum when it goes back, and that's a lot less damage to both cars in that case. Now, the innovation about colliding beams, and the idea came that if you have two beams of protons that collide head on, then you get all the energy into the collision. There's no recoiling that you have to cope with. And you get a lot more. You can imagine two cars colliding head on, 100 miles an hour, terrific smash. And much more damage, which turns, in our case, in the case of particles, into the creation of new particles. Now, that seems quite a good step to do if you can do it. But actually, it's even more important with particles because relativity means that energy and mass are basically the same thing. So the target here has got a lot of mass, if you like, as well as the beam. So this was the beginning of colliding beams. And that happened in 1971, shortly after I got to CERN with the machine called the intersecting storage rings, ISR. So they took the beams from the proton synchrotron, split it into two, and put it into this ring with two beams. You can see the beam pipes here. They're made to cross at 8 positions around the ring. And they're not completely head on, but they're nearly head on. One's coming this way, one's coming this way.
Mike, I have to let you know, nobody is able to see the slides. I can't get it to work yet.
Oh, dear. Okay.
I wasn't aware that you were going to be using slides, and I didn't set it up, so I'm still trying to get it to work. Just be aware of that as you're talking through. Try to be as descriptive as you can.
Oh, should I just carry on then and just try and with that? So
yeah, just try to be descriptive. You've done a great job so far, I think.
Okay, so what I've come to is the first machine that used colliding beams between proton beams, putting them almost head-on in collision, going around a ring in two separate vacuum pipes and colliding head-on. And that made collisions with a much higher equivalent energy than putting a beam on a stationary target. Now, as I showed before, protons are made of quarks and gluons, which are force particles that stick the quarks together. And so you can think of them as like micro beams. And in this machine, we collided protons together, and we discovered that sometimes the quarks inside the protons can scatter out to large angles. And initially, one thought quarks may be made free and come out of protons, kicked out, but that doesn't happen. They turn into jets or sprays of other particles. It seems that quarks are held together and confined. They never get free. This is the very strong force that's holding them together. In the bottom right of this picture, if you can see the slides, you see the experiment that I worked on, which had these blocks of actually uranium and plastic scintillator in sandwiches that were able to detect the particles come flying out sideways from the collision.
People can now see the slides, Mike.
Can I see the slides? So, okay, so I'm on slide, I'm not sure which number slide it is. It's number 4, it shows ISR. At the top right, you see a little diagram of the ISR's colliding beams. And to the left, you see a picture of the two beam pipes with the protons in collision. So this was really a step into the future high energy regime. And studying collisions between quarks and gluons. The next slide shows how can we see these particles? They're so small, so much smaller than atoms even. How can you possibly see them? Well, of course, we don't see them directly with our eyes, but we can make them visible. They can make tracks. So back in the 50s and 60s, before these colliding beam machines came on, people took photographs with a so-called bubble chamber. So what the bubble chamber was a vessel of liquid that's nearly boiling, but not quite. When charged particles go through that liquid, they ionize the atoms on their path. They kick electrons out of the atoms, leaving negative electrons and positive ions in a trail. And then by quickly expanding the liquid that was nearly boiling, it boils preferentially along where those ions were. And these ions seed bubbles, and they make a trail of bubbles that you can then quickly photograph, and then recompress it, kill all those bubbles, and go back to a non-boiling liquid. So this was making lots of beautiful photos. The tracks of particles are spiraling in because it's in a magnetic field, and charged particles going through a magnetic field bend to the left or right, depending on their electric charge. And the slower they go, the smaller the circle. So you see them spiraling in as they lose energy by ionizing the liquid. Now, this was labor intensive. People were measuring these tracks, and then we made automatic measuring machines. But the future was not with bubble chambers. The future was with electronic detectors. And the bottom right picture shows a reconstruction in the computer of a collision between two protons at the Large Hadron Collider. And all the orange lines coming out are tracks of particles. Again, the particles are much too small to see, but in this case, they leave electron ion pairs in gas and or electron hole pairs in solids like silicon and so on. And that goes straight into electronics and into computers. So we can record thousands of collisions per second. So then the ISR, okay, the next step in colliding beams was actually a very clever idea at CERN. They built a big accelerator called the Proton synchrotron, the super proton synchrotron. It was one ring. You see a picture of it down there. Big ring, and protons were accelerated around and around the ring. The brilliant idea was that if we could make a beam of antiprotons, which have a negative charge, we could put them in the same pipe but going in the opposite direction. And because they've got negative charge, if positive particles were going clockwise, these would go anti-clockwise, and you would have them both going around in the same pipe. Now, they had to be bunched beams in this case, little tiny bunches of protons and antiprotons. And making beams of antiprotons was very difficult, but the problem was solved. It's called beam cooling. And Van der Meer solved that problem and got the Nobel Prize for that. So they were able to convert this machine into a proton-antiproton collider and get much higher collision energies than we could get at the ISR. We got up to 540 GeV, whereas the ISR was only to 63 GeV. And this was enough energy now to make more massive particles. Remember, energy turns into mass in these collisions. To make a massive particle, you need a lot of energy. And theorists had proposed that there were these weak bosons I showed on the diagram before, the W and Z bosons that were the quanta of the weak force. But the masses were up at 80 or 90 GeV. That's much heavier than the proton GeV. So you need a lot of energy to make these. And they're also extremely unstable. So they decay almost immediately. And the bottom right, you see this diagram where the proton, I'm showing it as an up quark, a down quark, and another down quark. And the antiproton is an anti-up quark, and an anti-down quark, and an anti-up quark. There should be anti-down there. And so what can happen is when two protons collide, you can get inside them a down quark colliding with an anti-up quark, and they can fuse together and create this W minus boson. You see the charges work out. These quarks have fractional charge. Anti-up is minus 2/3, down is minus 1/3. That makes a W. But the W is extremely unstable. It doesn't travel much further than the size of an atomic nucleus and decays to an electron and a neutrino, or a muon and a neutrino, or another quark, and it can decay back to the down quark and the anti-up quark as well. So, and then in each collision, many other particles were created. But the W and Z production was very rare. Not many collisions produced them. It normally produced other particles, but it was like a needle in 1,000 haystacks to find these. But we did find them. They found them with a handful of events, but there were striking events. And Rubia, who led that team, got the Nobel Prize together with Van der Meer for discovering the W and Z particles, thanks to the high energy that he got with the collider. And then the baton was passed over to the Fermilab, which had a higher energy machine and was able to make it into a proton-antiproton collider. You see a picture here in the bottom ring. The ring's 4 miles around, it's underground, still there, of course, and the machine is still there, although it's not used anymore because the Large Hadron Collider at CERN made it redundant. This top ring is an older accelerator. The bottom ring is actually superconducting magnets that go 4 miles around, and they were able to get much higher energy collisions. So the CERN proton-antiproton collider was switched off when this came up, and this then took over the lead and had enough energy in the collisions to create these heaviest quarks that were known. The top quark had been predicted, but its mass wasn't known. At first, the mass, they thought it may be like 20 GeV, and then 50, and then 100. Finally, it came out as a very heavy particle, mass of about 174 GeV. It's the most massive particle that we know. And it's also very unstable. It decays in 10 to the minus 13 centimeters. That is about the size of a proton. There's a little diagram at the bottom. It's called a Feynman diagram, where a top and an antitop are produced. They decay almost immediately to a W and a B quark or an anti-B quark. Those in their turn decay into particles, jets. I said quarks don't become free. They turn into jets or sprays of lighter particles. So the result of a collision in this case would be an electron, a neutrino, which you don't see because it travels out, doesn't interact with anything pretty well. And then 2 jets from this quark and anti-quark coming from the W decay. It's very complicated, but eventually in 94, we found evidence for these events, and then confirmed by both experiments with 5 standard deviations, making a discovery in 1995. Each of these 2 experiments, similar detectors, but different techniques, actually had about 600 physicists, very international project. And then, so that was the highlight of this Fermilab collider. The next slide shows an aerial view here. This is it's in Batavia. You see it's the west of Chicago. It's this tunnel 4 miles around. There's various other beams of particles and so on. This is the Tevatron tunnel. This is the high-rise building called Wilson Hall, which I wish you could go into, but even I have to get special permission now because of COVID to go into it, but I have an office here on the 11th floor. Here's Enrico Fermi. He is named after him, but he died way before this was started. But he was so brilliant. You know, he built the first reactor in Chicago Squash Court and in the war and so on. So then now the baton passed back to CERN because they built this Large Hadron Collider, which is 27 kilometers around. There's about 17 miles around. Here you see a picture of the tunnel. It's superconducting magnets filled with superfluid helium cooling. That's 2 degrees above absolute zero. It's so cold that helium flows without resistance, and the magnets are made of, with, I think, niobium, titanium coils, superconducting. And the other energy gets up to 13,000 GeV. At Fermilab was 1,000 in each beam. Now it's 13,000. And the bunch of protons in this case, both protons direct in both directions. You don't have to make the antiprotons, which was a painful, difficult business. Protons come out of a bottle of hydrogen, basically, and they collide bunches of protons with about circulating around this big ring 10,000 times per second, because they're going at 99.999999 speed of light, and they keep circulating for about 10 or 20 hours, by which time the beams are now weaker because many of them have been killed by colliding. So then they can refill the machines. But it's an extraordinary machine, a huge accomplishment technically, the most complex machine we ever built. Okay, the space station is also big, but not quite as complex in a way. And here it is. Well, it's underground all the way, but here's a picture, an aerial view. You see at the back, you see Mont Blanc, the highest mountain in Europe. There's the Alps. There's Lake Geneva, the town of Geneva. You can see maybe here is the airport of Geneva to give a scale. And this is the position of the ring underground, 27 kilometers around, under the countryside. Here's the center of CERN. You know, it takes 20 minutes to drive over to where my experiment is over here, the CMS experiment, compact muon solenoid it's called. And there are 4 experiments, CMS, LHC-B over here, and Atlas over there, and there's Alice under there. So trillions of protons race around this 10,000 times per second in both directions and collide at those 4 places. And where they collide, they're focused down to a tiny beam like the diameter of a human hair. I'll say a bit more about that. Here's another nice picture of the machine. You can drive around in a little cart, not a real car, but all the way around. Here it's exposed to see between all these magnets, you have complicated cryogenic super cold connections. And when they first switched it on, 1 out of several thousand connections had a fault, and they had a big problem because several magnets got damaged and helium came in, and they had to spend a year fixing that problem. Here's another picture of one of these magnets, 50 meters long. It's a superconducting dipole being lowered into the tunnel through this oval shaft down to the tunnel. You see, and you have thousands of these things had to go down there. So the beams themselves are something like 30 microns wide. Think about the diameter of a human hair, and about 1 foot long. And they're separated by about 8 meters all the way around the ring in the 2 separate pipes that just are brought together at these 4 collision regions. So and they're steered around these orbits, a 17-mile orbit. And these hair diameter beams have to collide head on for hours on end. It's extraordinary how they control them. And there's about 1 billion protons in each bunch, but they nearly all miss each other, even though the bunch is the size of a human hair, because only a few collide each time. They're so tiny, they're 10 to the minus 13 centimeters in diameter. Still, in 1 second, we have about 1 billion inelastic collisions in each of the 4 collision points with these giant detectors, each with about 3,000 physicists. This is the other big experiment called Atlas. And these big things here are coils making a toroidal magnetic field. The other one is a solenoidal magnetic field. You may ask, where's the beam? Well, the beam pipe is not installed for this picture. It'll go right down the middle there, and detectors will be inside. But this just shows the magnet of that thing. And these are superconducting coils in that magnet. Very, very big project. And this is a picture of the experiment that I work on called CMS. You see the man down there. We have tiny men there, but and it's open so that you can see inside. But on the left and right, those 2 sides will be closed up for collisions to make it sort of hermetic device. And this thing weighs 12,500 tons. It's more than the Eiffel Tower. It's 80,000 crystals of a material called lead tungstate, which is transparent but very heavy. It's 98% metal by weight, but it's transparent. And when particles go into this lead tungstate, they make scintillation light. They make flashes of light, which are detected by photomultiplier detectors. So the whole thing has 700,000 electronic channels. And in 1 second, you write enough information for about 10,000 Encyclopedia Britannicas. It's all very, very, very wow thing. So, and then with this machine, not only we to make thousands and many millions of top quarks, but also discover a long sought particle called the Higgs boson that was found in 2012 at CERN by both teams, the 2 big teams, CMS and Atlas. And of course, it made the cover of The Economist, finding the Higgs boson. And here was the signal. It's a bump in this case, it's the mass. Two gamma rays that are detected, and you recombine the 2 gamma rays to ask what the mass would be of a particle that decayed to those 2 gamma rays. You plot it, and you get a continuum with a bump. And this bump is actually the first evidence for the signal for the Higgs boson. And it's shown in a different way by this plot from Atlas. Both experiments seeing the same thing, same place, made it really convincing. Now, what is the Higgs boson? Well, just briefly, it's a quantum of a field that fills the universe that has been proposed that gives mass to particles like the W and Z bosons and also to the quarks. This field unlike gravitational fields and electromagnetic fields, it has no direction, just a value. And it's the same everywhere through space, as far as we know. And particles, when they plow through this field, they pick up mass in a way that I can't explain. But then the Higgs boson decays. So how's it produced? There are many different ways it's produced. Two gluons, that's shown as these little spirals here, these gluons, one from each proton, can collide. And they don't actually couple directly to the Higgs boson, because the Higgs boson couples to massive particles, but it can make a little loop of top quarks here, and that can go to Higgs boson. It's called a top loop. Another way is actually top anti-top fusion, or a W or Z boson can radiate these things called Higgs trouble. There are different ways the Higgs can be produced, but it's a very rare thing to produce it, and then it decays in different ways too. It can decay to two Z bosons. Actually, it doesn't have enough mass to decay to two real Z bosons, but it can decay to one real one, which decays to a pair of electrons or muons, and the other one, which is not real, it's not got all the mass it should have, but it can still decay to a pair of electrons. So that would give you 4 of these electrons or muons, or in the final state, and you can reconstruct it. And then another way is for the Higgs to decay to 2 gamma rays, and that was the plot that I showed you before. It does it through a top quark loop, which is sort of popped out of the vacuum. The Higgs is lighter than 2 top quarks, so it can't really happen like this, but you can have a vacuum fluctuation to produce that, or again, a loop of W's and so on. So this is a picture of an ATLAS actually event where they've reconstructed the tracks, and these 2 green things are 2 photons, 2 gamma rays that have come from one of these processes here. And you have to collect lots of events like that, plot the masses, and see if you see evidence for an excess. So here's another picture of the compact muon spectrometer, which is the one that I am privileged to work on. You see the size, I mean, it's like 6 stories, chock full of electronics. And it's in a way like a huge digital camera recording tracks of particles created in the collisions. And now, at the moment, the Large Hadron Collider is down for 1.5 years, being improved and upgraded. They're going to push the energy up a little bit. The detectors are all being improved and upgraded as well to cope with higher luminosity, which means more and more collisions per second. Instead of like 1 per billionth of a second, is going to be like 20, 30 per billionth of a second. And then we have to electrons to cope with that. And that will be coming on the air next spring. Better, bigger, and well, not bigger, but better. And there are thoughts and plans and ideas to make a bigger collider still that would go right under Lake Geneva, a much bigger one, but that's just a study at the moment. Because there's, as I said earlier, there's lots of things we don't know. These particles only make up 5% of what we know, and we think that there must be other particles, other forces, and so on to discover. Just before I finish, I want to give a shout out to global collaboration in science. As you see, CERN users are from all over the world, except not much from Africa, but otherwise. The blue states are the CERN member states, Europe. This is actually out of date, it's 2013 or something, but the green states like the USA and Russia are observers. We have a seat on the council, and we pay not the subscription, but we pay our share of the experiments and the machine. Fermilab makes magnets for the machine, some of them quadrupole magnets. And then there are all these other countries who have physicists who participate in the projects, in the experiments. So vast number of people. And I think it's amazing that, everybody can work together, because science is, it's not religious or political in some way. So it's easy to work together. Easy, I say. We collaborate. We manage to collaborate. Of course, it's competition too, but there we are. And there's more than 1,000 US-based physicists who work on the Large Hadron Collider experiments. Thank you. So I'm open for questions.
Thanks, Mike. Scott had to step away. He had an emergency, but I assume he'll be back in a little while. But thanks again for a great presentation. My first question actually is about the rate of collision. You said like 1 billion collisions a second, but you said that it's colliding at 4 points and the particles are going round the ring 10,000 times a second. You're getting a lot of collisions at every point. Like, so when you're looking at a snapshot from one of the interactions, or one of the passes where we get the beam interacting, how many inelastic collisions do you see at a time that you have to like separate out?
Right. So the electron, we have to have the detectors gated at a level of about 25 nanoseconds. So we see the particles from one collision, one beam bunch collision. So if a beam bunches collide, the bunches go through each other. 25 nanoseconds later, another bunch will go through each other. And every 25 nanoseconds, a bunches go through each other. So we have to, of course, the particles are still flowing through the apparatus when the next bunch comes along. So we have to all time that carefully. And some detectors are actually sensitive to more than one bunch crossing. Now, in each bunch crossing, we have typically roughly 25 collisions between protons in the bunch crossing. So that makes quite a mess. Now, we're able to, the collisions are spread out over about 25 centimeters or so in space. So we reconstruct the vertices to try to unravel. There's a problem because sometimes two collisions can be so close together that we can't separate them, you know. Now, for some things like when we're producing top quarks or Ws, they spit out sideways very high momentum particles, and you don't need to matter which collision they actually came from somehow. But yeah, now it may seem with, let's say at each of these 4 collisions, actually, to be honest, 2 collision points with the 2 big ones, they have the highest luminosity. They have 25 collisions every bunch crossing on average. The others are down to like 5 or 8 collisions per bunch crossing, so they don't have quite so many. But still, so you're using up, the beams are being used up, and but you put in 10 to the 14 protons in the beginning, right? So 10 to the 14. So if you're losing, you know, 10 to the 9 is 1 part in 10 to the it works somehow. The math is hard to do in your head, but there's at each of the 2 big collision points, yeah, there's about 25 collisions every 25 nanoseconds. That's 10 to the 9 collisions per second, and it's going to get bigger than that.
That's pretty amazing.
Yeah.
Does anyone else have any questions? While you're talking, I'm going to go and see if there are any questions on YouTube.
It's really amazing to me because I actually worked on electron-positron collisions as a freshman at MIT in 1969 and 70. And I worked on building spark chambers for Cambridge Electron Accelerator. And when they got that system working, they were getting 1 or 2 collisions per day.
Yeah.
Not 1 billion per second.
Yeah. Yeah. Yeah.
The field has come a long way.
Yeah. I should say that this electron-positron collider happened before the CERN ISR, but by a few years before. And yes, it was very, and of course the electrons and positrons, they have a much smaller cross section than protons, so the rate of collisions is small for the same beam intensity. But yeah, we've come a long way.
Yeah.
Now, the Large Hadron Collider was actually interesting. You mentioned that because it was built in the same tunnel that a previous electron-positron collider had been built in. That was called LEP, the Large Electron-Positron Collider, and that put in electrons and positrons around, and was able to tune the beam energies so that they could make directly the Z boson, 90 GeV Z boson. So they had 45 GeV on each beam. Electron positron could collide and annihilate and make Z boson. So they were a Z factory in a way. They made, but yeah, and then that was the first machine in that tunnel, and then that was taken out to put the Large Hadron Collider in the same tunnel. So the tunnel was there. Yeah. Some of us actually wanted the proton collider in first, but we lost that battle. But the electron collider got in first. Yeah.
Well,
The whole thing
you
of
had to
going
make
through-
advances in the instrumentation. I mean, you know, in 1970, we had a spark chamber that made visible sparks, and we were taking pictures.
Yeah. Well, I was before that in 1969. My thesis experiment, I had spark chambers too, but I made a wire grid for one of the electrodes.
Yeah.
I recorded the signals on the wire grids.
Yes, we were a bit old-fashioned.
Yeah.
I have since then worked with similar wire grid systems for X-rays.
Yeah.
I guess we should.
The CERN is going through an upgrade. How high is it going to go, and what do you expect to see once the upgrade is completed?
Right. So the energy upgrade is not very much. It's only going from a total of 13,000 GeV to 14,000 GeV. That's not much, but you have to push every magnet to its limits. The main thing is going to get 10 times more collisions per second, so we can see even rarer things, right? And the other thing is that detectors have to catch up with that. So the detectors are being, parts of them, upgraded to be able to cope with this higher rate of collisions, to have not 25 in a bunch crossing, but 125 in a bunch crossing, or more, 150. Actually, the nominal is 150 per bunch crossing. And I'm actually working on, my project I'm working on is to look for dark matter particles that may come out and go through 50 meters of iron in the magnets and then decay beyond that. Actually, they're not dark matter particles, they're so-called portals to the dark matter side. Anyway, another thing I didn't mention was that CERN is able to put heavy nuclei, fully stripped nuclei like gold or lead, into the machine and collide nuclei together. And of course, because they've got much bigger electric charge, they get a lot more energy on the nucleus. And colliding these two nuclei together, they're creating collisions that we haven't seen in the universe since the Big Bang, right? And so the idea is that when you collide two nuclei together at such high energies, the protons and neutrons are squeezed out of existence and make a plasma of quarks and gluons very briefly before it explodes again. So it's like a phase transition. And that's what's being studied. It's clear that I think there's good evidence now that we do make a quark gluon plasma, which is not, the protons and neutrons are sort of melted together. But it doesn't last very long because they immediately turn back into protons and neutrons. But that's also been done. I mean, it's amazing that you can fully strip lead nuclei and put them into the Large Hadron Collider. So
we should probably explain to everyone what is the trade-off between using between an electron-positron collider and a proton-proton collider, because electrons and positrons are very simple.
Yeah.
Right.
Right. So yeah, so they're very simple. So they make very clean collisions compared with a proton collider, where it's the quarks that scatter, but they're surrounded by, they're not free, they're surrounded and they're imprisoned and confined inside the proton. So they come along with a lot of baggage, a lot of the other quarks and the gluons and so on, a lot of baggage. So you don't get such clean collisions. On the other hand, when you put a charged particle in a ring like this, it radiates gamma rays. You can't accelerate a particle without it radiating gamma rays. And electrons radiate gamma rays a lot more than protons because they're much lighter. And so they're going much faster for the same energy, actually. So in that big tunnel at CERN, this 16-mile around tunnel, the electrons, they could get them up to an energy limit of about 80 or 90 GeV per beam. And we're now at 7,000 GeV per beam. And we can do that because the protons are much heavier than electrons. They don't radiate gamma rays as much. So you don't have to keep pumping energy. You have to keep pumping energy into them because they do radiate a bit, but not anything like electrons do. So now people are looking for a more energetic electron collider. You'd like to have one that is energetic enough to make Higgs bosons. And you can do that by colliding electron and positron and making W's and Z's, and they radiate Higgs bosons, and you can make a sort of Higgs factory. This is an idea. But instead of making a big circular machine, people talk about a straight line machine, a linear machine. So you collide beams in a linear clip. Now, that seems very wasteful because you only collide once and then they're lost. Whereas in a circular machine, you go again and again and again, you have many more chances. But there's a project called CLIC, CERN Linear Collider, which is still on paper, but it's being designed. And the Japanese want to do one as well, or instead of. So somebody would do that. I don't think there'll be two. The Chinese are also interested in this. So, but electron and positrons together, very clean.
One man's physical problem is another man's physical opportunity. These days, as an X-ray person, I make use of synchrotron radiation as a calibrator for X-ray instruments. Because all that radiation that comes off the electron synchrotrons is very useful as calibration. And of course, nowadays the molecular biologists are making good use of this, where they get bursts of X-rays that are sufficiently intense that they can get diffraction patterns off of single molecules in the time before the molecules disassemble from all the X-rays. So you send a picosecond burst of X-rays at a molecule, and you can look at its structure.
Yeah, two colliders I didn't mention, but you reminded me. So there was electron-proton collider at Daisy in Germany, Hamburg, and they built an electron-proton collider. And they used the electrons as like an electron microscope to see inside the proton in great detail. And that was very interesting. It did measure the structure of the proton in enormous detail. But then they turned that off, and they've used the machines to make intense X-rays. So it's now an X-ray source. Very high intensity beams of very small spread X-rays. And then at Brookhaven on Long Island, they have another machine called RIC, Relativistic Heavy Ion Collider. And they collide heavy and nuclei together. And they do a bit of proton-proton together as well. But now they're teaming up with Jefferson Lab near, so at Newport News, and they're going to make in that tunnel an electron-proton collider there, an electron-ion collider, EIC, electron-ion collider. So they have electrons in one ring and heavy nuclei in the other ring, and it's a sort of super microscope to study matter in enormous detail there. So that's a project that's happening in Brookhaven, actually.
And it's not always super intense for calibrating sensitive X-ray detectors like the ones on NICER on the International Space Station. We took some detectors to Bessie, and we calibrated them with typically half a dozen electrons in the ring, because that was the kind of flux we could handle. And we would notice if we lost an electron.
Well, you don't get the record for the lowest intensity beams because my friend Jerry Gabrielsa has been making a beam, actually an electron going around a magnetic field in a trap, just a single electron going around in a trap, and also a single antiproton. He got single antiprotons in a trap and keeps them there for weeks or days or whatever. So, and that's super interesting for measuring, the properties of electron, like has it got a magnet, has it got a dipole moment, electrodipole, things like that. Very interesting. So, yeah.
So the accelerators, the relationship in quantum mechanics between the energy of a particle and its wavelength. So the greater the energy, the smaller the wavelength. So these are really like microscopes. When you bring the energy up, you have a small enough wavelength to be able to see things on the order of that wavelength. Because otherwise, it's a bit like trying to, if you have a little canoe in the ocean and there's a tidal wave passes underneath it, you're not really going to be able to identify anything about see that boat in the wave as it passes through, right? Because the boat is just going to ride the wave. But if the waves are smaller than the boat, then the wave will be disrupted by the boat more. You'll have more of an interaction. So it's a very similar sort of relationship in accelerators, and that's why we want more and more energy. As we get more and more energy, we're seeing smaller and smaller things.
Right, and we have shown that the size of the quarks is smaller than a 10,000th the size of a proton. Now we think it's probably much more than that, but that's what we've shown by studying scattering of electrons on the quarks, and also here's a thought. So you see, we've got these superconducting magnets that can bend these protons round in a circle, but the circumference is, it's 16 miles. And yet they can be kicked sideways by another quark inside the proton. The force is billions of times more than the magnetic force on these particles, because that's the strong force when they get really close together. Now, it's also more complicated because the strong force actually has a property of getting stronger the further away. It's like the end of an elastic band. Take an elastic band, there's a force between the ends. It's not a very strong force until you try and pull them apart, and then it gets stronger and stronger and stronger. And then eventually the elastic band snaps. So you can't get the end of an elastic band free. It's always got two ends. Anyway.
We have a question from YouTube. Brett asks, as far as the scintillation detectors you mentioned, are they using photomultiplier tubes, or are they moving toward digital detectors using CZT?
Right. So those lead tungstate blocks they did use avalanche photodiodes, which are like photomultipliers but are simpler. Now we're moving more to silicon photomultipliers, which are solid state photomultipliers. But those still have avalanche photodiodes on that. The sort of classical glass photomultipliers that have these dinodes in and so on, they still have some applications because they're more radiation hard, but bigger and clumsier and more expensive. But now we more use silicon photomultipliers, which are quite cheap. You can get them for $20, in quantity, and they're now fairly radiation hard, which is an issue. So we're using those more. Yeah. Any other questions in the chat?
There are no other questions on YouTube.
Okay, and Scott is back.
Yeah, at least for a few minutes.
Okay.
Mike, you may have already covered this. I had a curiosity about why is it in Fermilab they use protons and antiprotons to double the energy, as it were, but in the LHC they use protons against protons.
Yeah. So the idea of using antiprotons, which was a very clever idea, but you have to make the antiprotons to put in, and it takes hours and hours to make enough antiprotons to make a beam. So to make antiprotons, you take a beam of protons and you put them in a metal target, and the energy of the protons on the target steel, nuclei or whatever, makes all sorts of particles. Among them, there's a few antiprotons, a few out of thousands. They're negative, and you can collect them with magnets and so on. And you can build up a beam of antiprotons. And the trick of Rubier and Van der Meer was that they could do that, and they could turn this SPS proton synchrotron, which existed, into a P-bar-P, a proton-antiproton collider, without having to build a new machine. They had to build a new antiproton source for that. And so that was a cheap way. But on the other hand, it's very time consuming, and you don't get such intense beams with antiprotons. You can get a beam of 10 to the 13 antiprotons, but you can switch on the tap from a bottle of hydrogen and get 10 to the 15 protons in no time at all. So it's so I was actually on a study group for the super collider. I didn't mention that. That was a thing that didn't happen in Texas. The super collider. That was 20 TeV per beam, and it was supposed to be near Dallas in Texas, and they started it. It got cancelled by American government. It was after building, they built a third of the tunnel or something like that, but costs were getting expensive. It over-costed, and it was initially on a greenfield site, which was a mistake. I mean, if they put it to Fermilab, it would have saved a lot of money. But it was sort of pork, if you like, to put it in Texas. And also, it was seen as an American machine, our answer to CERN, and yet these things are so expensive, they should be done internationally. And So, I may be naive about this, but they did ask, Japan, India, China, will you join in with it? But it had already been designed and we were just running out of money. So we asked them for money, which was not the way to do it. So that didn't happen, that machine. And then that machine, it was motivated finding the Higgs boson, which we managed to find at CERN with a low energy machine, but higher intensity beams, and we managed to do it. But we didn't know the Higgs boson mass at all very well. It could have been anywhere. And at Fermilab, we looked for it, and we managed to show regions where it wasn't. We could exclude certain mass regions of it. We nearly got there, but without the intensity that the CERN machine had with their proton-proton collisions, we didn't get enough evidence for it. So that came from CERN. Now we're pretty sure there's other particles out there. The so-called supersymmetry predicts a whole load of more particles that we have been looking for and not finding. So either they're much too heavy or they don't exist. And these new particles that we're looking for, like dark matter, may actually be quite light particles, but just very weakly interacting. So they're very hard to make. So that's where my hopes are in finding them. Maybe,
I have one comment and one question. My first comment is, and I always like to point this out when people talk about dark matter and dark energy being most of the universe. It's most of the universe by weight, not by how much we know about it, right? So, because it always comes up in a conversation whenever you tell someone something that we know about physics. They'll throw it back in my face like, we don't even know 95% of the universe. Okay. And I'm like, well, by weight, but we actually know a lot.
Right. And dark energy may be very simple. It may just be some, cosmological,
right.
Or it may be more complicated. It may have particles to do with it, and it may not. I don't know. We don't know. Dark matter also, we said we're looking for dark matter particles. We do know dark matter exists because it's holding galaxies together and it's bending light, and so on. But it could be a whole spectrum of particles, and it could be particles that hardly interact with our particles at all, like some parallel universe sort of thing, almost, and it's even possible they don't interact with our particles at all, except through gravity, and then it'd be very, very hard to find them. But the hope is that they do have some connection with our particles, and we can produce them and discover them.
Well, one of the people I like to follow on YouTube is Sabina Hossenfelder, and she says some things that are kind of controversial. One of them is that she doesn't think that building bigger colliders are a good investment. And I'm wondering if you have an opinion on that issue.
Is this off the record? No, can we turn off?
It's a difficult question to ask an experimental physicist, particle physicist.
Yeah.
But, there is an issue of diminishing returns, I guess. Adding more intensity to the LHC sounds like a really great idea. You've already got all the equipment. An upgrade will means that you just get much better statistics, right?
Yeah. I think at this stage, to say, people give talks saying this 100 TeV collider that CERN is looking at is a no-lose situation. We'll either discover new massive particles, or we'll discover other secrets or whatever. And I don't really subscribe to that viewpoint. What we really would like is to have more innovative techniques that maybe you can get. People talk about different ways of accelerating to get much more gradient per GV per meter, stuff like that. Innovative techniques, and then there are experiments that don't use accelerators, looking for dark matter particles coming from the sky and into cryogenic detectors, recoiling nuclei and stuff. So, and again, if these dark matter particles are actually light, then you don't need more energy, but you need more intensity. You need cleverer techniques. And there are many experiments now looking for them also in the fixed target machines, which can have more intensity. So I think that it would be personally to say, right, we need to go to build a 100 TeV collider now. Actually, they talk about first in that big tunnel putting an electron positron collider, and then we know that you can make thousands of Higgs bosons and study them. So the standard model predicts exactly the decays of the Higgs boson. It decays to bottom antibottom quarks, and we've measured many of the decays, and so far it agrees with the standard model. But we haven't measured all of them, and it's quite possible the Higgs boson decays 5% of the time to dark matter particles or something like that. Now, in an electron positron machine, which will be the first one to go in that big tunnel, we can study tens of thousands or hundreds of thousands of Higgs bosons in great detail. Then, you know, that doesn't have the energy. That has an energy of, well, the central mass energy is about 300 or 400 GeV. I don't know, but it's, as you say, very clean. Electrons and positrons, very clean. I don't think, well, so what can I say? I mean, it's, the other point is though, that when one builds these big machines, you push the limits of technology in so many ways. I mean, for example, you know, the amount of data we are storing and transmitting around the world, stuff like that, the way we cope on it, we're developing, you know, artificial intelligence to look at the events in some way. We're developing, pushing the edge of technology very far. I mean, this is the biggest superconducting device ever built. And we push technology to make magnets, cheaper, better superconducting magnets, which you find in hospitals, right? Now, I'm not saying the LHC has been pushing that. Certainly Fermilab did. When Fermilab built the Tevatron, we had to push to get cheaper and better superconducting magnets. And that did have an effect on the MRI scanning industry and so on and so forth. And so
CERN invented the World Wide Web.
Exactly, that was invented at CERN, right? So we all use that, right? But yeah, and yeah, there's a lot, when you got lots of smart people there trying to solve a problem, like, you know, how do you record billions and billions per second of these complicated things and sort them out? So you can't look at those events. You have to have smart artificial intelligence or whatever looking through them. I don't know.
A lot of my career has been recycling the technology out of high energy physics into astrophysics. The wire proportional counters, the Hitomi mission I recently worked on with the Japanese. I was using, I designed measurement chips, and I was using a library that I actually got from Keck of components for measurement, for charge measurement chips, things like that. The other thing that's happening in astrophysics, though, is that we're learning to do more with smaller things. I'm involved with NASA's new Planet Finder TESS, and it's a much smaller thing than its previous Planet Finder Kepler. I mean, the TESS cameras are this big. Kepler was a big telescope, was a huge telescope. And so there are opportunities to do more by being smart and doing small things. Another example is NICER on the International Space Station, where we have 56 simple telescopes ganged together, and it's much cheaper at doing what it's doing than a single big telescope would be. And much easier to build and all that. So there are ways, there are opportunities to do things with smaller stuff. I'm not against big science projects, but I worry, some of them, I worry that they take away so much of the oxygen from the system that the small ones that both can make discoveries and can feed into the next generation, the big ones, don't get the attention that they deserve.
Yeah, there's another aspect. I mentioned that China and Japan are interested in future accelerators, and they are actually. So this would be, so as I said, the world will not build two linear accelerators of that scale. And if China just says we're going to do this, if you come into it, then it's an opportunity. I mean, politics gets in the way, but we managed to get all European. I mean, CERN was started in the 50s when European countries have been killing each other, right? And it was after the Second World War, and we got, because science is international, we got all together to do this together, and now it's worldwide projects. And I had before, in the Soviet era, before the fall of the Berlin Wall, we had Russians and Chinese and Israelis working together on our project at CERN. They could do that, and so this is about worldwide collaboration. Another thing I didn't mention about energy. So there are higher energy collisions in cosmic rays. They come from outer space, and they have even higher energies than we can get at the Large Hadron Collider. But they're rare, and so you can't put a detector at the top of the atmosphere and get to the top energies. So I've been part of a project with the Auger collaboration, and these cosmic rays come in from outer space, and they've got huge energies, and they make a shower that spreads over many square kilometers. So we put 1,600 water tanks over an area 3 times the size of Chicago, and see flashes of light in several tanks all at once that's come from a cosmic ray. Very interesting project. Another one is Antarctica, under the Antarctic ice, looking for flashes of light from neutrinos. These are not collider physics, but they're different windows into the science, and so it's very interesting. Do these collisions of these cosmic rays look unusual, or do they look like what we expect them to look like? And they're not such expensive experiments. I mean, compared with the Large Hadron. I mean, the Large Hadron, nobody asked me how much it costs, and I wasn't saying that. I'm not saying how much it costs, but the cost is shared by many nations. It's like a cup of tea per person in the European Union to pay that. So yeah.
When I was a graduate student, everybody was telling me, if you want to get a job, you need to be doing SSC physics. This is superconducting supercollider. That project got canceled about 2 months before I was done with my thesis. But there was an idea going around even back then, and I don't know how far it's progressed, if at all. Wake field acceleration.
Mm-hmm. Yeah.
And it's this idea that you can accelerate charged particles with a plasma, and in theory, you can get gradients like 1 TeV per meter. So you could have a relatively small facility and create the same kinds of energies as the LHC. But the fact that we're talking about building colliders that are even bigger than the LHC suggests that it hasn't come quite that far yet.
Yeah, Wakefield, that's one of the ideas. And it's still being worked on, and you can get very high gradients, but the beam intensities are extremely low. So no hope of colliding beams. But you could do maybe fixed target experiments with them. That is certainly, but because I say anyway, yeah. That's a clever idea. And so actually Click uses an electron beam. I don't know. It uses a wake field of one electron beam to accelerate another beam or something. It's outside my competence, but yeah. Another spin-off, I'm just thinking of a thing called Medipix. So detector developers developed a chip called Medipix, and it is going to make cheap 3D imaging MRI scans, I think. Maybe John knows more about that. I'm
working on a space mission that is intended to use it, actually.
Yeah. But when you go to an X-ray, you have an X-ray, it's a black and white X-ray. Well, wouldn't it be good if it was in color and fast, low exposure and 3D, So, and Medipix can do that. It's very sensitive, and it can measure the energy of X-rays as well, so it gets a lot more information, stuff like that. And that's a spin-off, yeah. But that's not why we do it.
I think that when I was one of the other things that helped me make my career decision was supersymmetry. That that really was what I thought was going to be exciting about the LHC, right? I was pretty confident we were going to find the Higgs boson. But there was a lot of interest in finding all these other light particles, an entire zoo of light particles, right, that would solve certain problems in the standard model. But although there would be this zoo, it would make things much more complex, right? So as a theoretical physicist, what we would really like is a very nice small equation that has like 3 constants in it. And there's just one particle, it's just strings. And everything else is just some vibration of strings, right? So it all becomes unified into something very simple. And if the LHC worked, well, now we'll have an entire zoo. If you thought the standard model was complicated, now we'll have twice as many particles. Of course, it's still, I mean, it would be a very, very beautiful symmetry to have discovered, but it was going to be somewhat more complex. And now it looks like we haven't found any, right? We're getting to the point where we think if there is something heavier out there, it won't solve the problems the way we want it to. Is that right?
Yeah, I think that's right. There are reasons why it's supersymmetry. I mean, it's a very beautiful extension of the theory to have the symmetry between particles that have one spin and particles that have a different spin. So so the electron would have a partner that has got 0 spin called the selectron. But because we haven't found it, it must be, if it exists, much heavier than the electron. So that symmetry is actually badly broken, but okay, symmetries are broken. And it's not natural for supersymmetry to be much heavier than TV scale. That we wouldn't find it at the LHC, but we could find it at a supercollider. It's not natural, but it's possible. But yeah, I mean, we still have not. Again, we have these 6 quarks and 6 leptons. There's 12 particles. They've all got different masses, and we don't know. We don't have an equation or a theory that gives. I mean. That predicts that mass spectrum. Maybe it's just some random spectrum or something like that. In the multiverse, they may be different, but you know, that's a challenge to the young people to understand that spectrum. The neutrinos are the only ones that don't have any electric charge, and they're much lighter than the others. So you might think electric charge has got something to do with it, but on the other hand, here's the thing: like the up quark and the down quark have got almost the up quark actually is a bit less mass than the down quark, even though it's got twice the electric charge. And it's good it is like that, because if it wasn't like that, the protons would decay to neutrons, and then where would we be? We'd have no hydrogen. So, and yet the others, the top quark's heavier than the bottom quark, and the charmed heavier. The charged 2/3 quark is usually heavier than the charged 1/3, but not in the up and down case. And that is odd. It's odd, and yet it allows the proton to be stable. And the neutron decays.
So once you have more statistics at the upgraded LHC, what are there some specific interactions that people are going to be looking at to find deviations from the standard model?
Yeah. So there are theorists have thought up many possible particles that we should be able to produce. One is heavy neutral leptons, which is like a neutrino, but heavier. Okay. And it should have more than 40 or 50 GeV, so that Z doesn't decay to it. One is axions. An axion is a particle that's been proposed, which can explain why the strong interaction doesn't violate CP conservation. The axions could be massive enough, or they could be extremely light. And then there's so-called dark photons. A dark photon is like a photon, but it couples much more weakly, 1,000 or 1,000,000 times more weakly than normal photons do. Otherwise, it's similar. So these are all particles that are that I and my colleagues will be looking for. Okay, because they interact weakly, they can penetrate lots of iron, but they can be, if they're produced, they can decay. unless they have to be produced in pairs. So anyway, experiments are looking and are ruling out regions of mass and strength, some, but there are regions that are not looked in yet, so we need to look there. But and then it may be that you know, we should get about 100 times more data than we've got now already. So over the years, it's planned to run till 2035, I think, the LHC. It's got a lot of life in it, yeah. Well, it's 30, it's 3:30 now, right? So
Yeah. Well, thanks again for your presentation, Mike.
you're welcome. Thank you. So we meet in 2 weeks, right? In 2 weeks.
Hope to see
Yes.
you at Fermilab some of these days. I mean, I
That'd be
miss going out there and visiting with everybody, and
I
and
know. You do.
it's fun.
Me too.
Too.
Yeah. Okay. Bye-bye, everyone. Bye.